Yeah, I think we're on top of the hour. Nice to see everybody again after a short break. I don't know if any of us attended SIDA meeting the last time. It's in June last month. So
Hi, Jana. How are you doing?
doing well. Jose, how are you?
I'm doing good. Can you hear me? Of course.
Perfectly.
Great.
Sounds so good.
That's
So
the best.
yeah, we're going to start shortly. And I'm just trying to admit as many people as we can into
Yeah,
the,
sure.
yeah,
We could leave some time.
right.
Okay, I will be here. I will be paying attention whenever you call my name. So I
Yes,
will
yes,
start
yes. No
talking.
problem.
Okay.
Mhm. Let's wait a little bit more for others to join us. Maybe 2 more minutes and get started. So, and then, I'm going to transmit the host power to you. You cannot go off. So you can help me to admit people,
All
if
right, sir.
you have the
Good morning,
admission
sir.
power. Yeah, to admit people. Why? In case okay. So let me see if I can do that. There you go. Yeah. So you are now the host. We can admit people as they come in.
All
Can you
right.
do that?
Yes.
Thank you. Yeah.
Yes, sir.
So I'm going to get started. Let me share my screen. Just going to share everything. And PowerPoint. There you go. So allow me to do that. So welcome everybody again to the 16th CONGA meeting. We do have this meeting every last Wednesday of the month. We gather here to discuss the CONGA initiative, and our our speaker this morning is a well-known person as well. So I'm going to give you a little bit about him in a short while. He's going to talk about the development of ScintPi, a low-cost GNSS-based sensors that was created by UT Dallas, University of Texas, Dallas, for the purpose of monitoring the ionosphere. So I'm going to give you a little bit about him a little bit in a short while, but the initiative is to um, the CONGA initiative is to help fill the hole in the central or equatorial region of Africa. As you can see in the pictures here, in the figures here, you have that large hole. And this is a very famous figure now because almost all of us are familiar with this figure. And the purpose is here is to just motivate us to see how possible a different equatorial region could feel like. So we have that distribution shown in the figure below, where you have different dots that indicate university, technical colleges, and high institutions that we can install these receivers. So the initiative is to build a self-sufficient or autonomous receiver that could be distributed across the equatorial and low latitude of Africa. And then we can have that feeling of data analysis and equatorial region globally. I mean, when you talk about the dynamics of the ionosphere, you talk about the equatorial and low latitude of the ionosphere. And then if that thought is not complete globally, we are still missing some aspects. And Africa happens to be the largest landmass in the equatorial region. And that is why we are pointing at this region, which is currently deprived of instruments, ground-based instruments for this kind of study. And this meeting, as you know, it helps us to build a network of people that can work together. You know, that's the primary reason why we are here. We want to train and develop people or members of CONGA to be able to use the ground-based instruments when they are installed. When you know the purpose of something, it makes it more admirable, and you can appreciate it more, and you can help to keep it safe. So that is the purpose here. You will bring in special guest speaker, people that are versed in this field, and people that are also working on this kind of instrument to talk to us so that we can get to the understanding of how this instrument works, how we can make it useful for our studies or for our research or for our projects or for our students or graduate students that are in need of all these instruments, grant-based instruments. So this is the purpose of CONGA meeting every Wednesday, and I think it's very, very good. I've received a lot of positive feedback about this meeting. So it is something I'm proud of to host this meeting every last Wednesday of the month. And one other last thing that we want to ensure in this meeting is the distribution of data. We want to make data accessibility available, free and available to researchers, scientists that are willing to use this data. There are some challenges right now about how data has been distributed. Some are covering or hiding the data or using it for themselves. But we want to encourage the accessibility of data freely for scientists, particularly for researchers or professors that are having students that are doing these studies, because it helps them to understand a global ionosphere. And when we distribute our data in such a way, it also helps us to get the usefulness of that instrument when other people can use it. Now, we have a lot of speakers that have been outlined, and these are our speakers from March to October. Just to tell you that October is the final, it's going to be the last meeting for the year, because in November in US we have Thanksgiving, and it is always the same week of our meeting. So excuse me, please. Okay. It's always in the same week of our meeting, and therefore we have canceled that meeting for the week. And December, of course, we know that is Christmas period, so it's always not available for our people. So before I give the floor to our speaker for today, I want to give a little bit of his background. And Dr. Josemaria Gomez, Josemaria Gomez was born in Piura, Peru. He earned his BS, that is Bachelor degree in Electrical Engineering from the Universidad de Ciencias Aplicadas in Lima, Peru, in 2016. Afterward, he worked at the research engineer at the Jicamarca Radio Observatory in Peru. He's a Peruvian guy until 2019. Jicamarca Radio Observatory located at the uh, magnetic equator. So the radio observatory, I don't know if you know that radio observatory is located at the magnetic equator where some of the students are currently learning and having some internship. So he's dedicated to providing observations of upper atmosphere and ionosphere. And during his time at the Jicamarca, Josemaria contributed to the project. So several projects focus on developing instruments for remote sensing of the ionosphere. In the fall 2020, he joined the University of Texas, Dallas, and the Upper Atmosphere Remote Sensing Lab, led by Dr. Rodrigues as a PhD student. Under Dr. Rodrigues' academic supervision, Dr. Josemaria conceptualized and developed the ScintPi 2.0 and 2.3.0 monitors, along with tools for processing, measurements, and managing data. So there was a time I met Dr. Josemaria along the poster boards, maybe one of the conferences at the AGU or CEDA, and I was like, oh, I forgot your name. He said, just call me ScintPi. So this is to tell you how he is passionate about this instrument. He worked on this instrument throughout his PhD, and he has published several papers. I've seen two of those papers, and those papers shown the usefulness or the importance of this ScintPi. And the ScintPi, as you will see from him, is as low-cost receivers, and that is part of what we are trying to do to distribute across the region where we can have, but in our case, we want to make it a autonomous powered. But what I mean by that is our instrument is going to have a solar panel and a different kind of network service. So that, given the situation and condition of the region, we are supplying these instruments. So right now, Dr. Josemaria is a research scientist at the University of Texas at Dallas. And I will want to, at this point, invite him to share his screen so that we can have him on the floor.
Thank you, Joanna, for that introduction. And I'm gonna share my screen now. Let's see if this works. Ready to share your screen. Okay. So give me a second. I have to allow this. I might need to rejoin, okay? Because the Zoom doesn't allow me to share my screen. Give me
no problem. Yeah.
1 minute.
So let me see. There is if you notice, we have a change in the link. So going forward, I think that is the link we'll be using for the meeting. I just want us to take notes, and I will send us a different calendar that we can access easily. I think Dr. Gomez is going to log in. Okay, there you go.
Okay, let's see now. Oh yeah, I believe I am sharing my screen.
Yes, sir. Yeah.
So let's see this. Can you see my screen and the slides?
Yes, we can. I think I can see it. I believe everybody can see it as well.
Okay, that's good.
We can
Okay.
see.
Thank you, Jonah, for inviting me. I am really glad to contribute to the CONGA project with some suggestions and alternative of low-cost monitors. As you say, my name is Josemaria Gomez Socola. I am originally from Peru. I joined UT Dallas around 2020, and then I started working with Professor Rodrigues since then. Well, today I'm going to talk about ScintPi, which is an alternative low-cost GNSS-based sensor for ionospheric monitoring and studies. This sensor was developed at the Upper Atmosphere Remote Sensing Lab here at UT Dallas for many applications and also for giving hands-on experience to the students. So let's see if I can. So today I'm going to talk about different topics. We're going to start with the description and motivation of ScintPi. Then we will talk about the development and the architecture of the system and the network that we have. And finally, I'm going to show some research studies that we have developed in the past. So to start with, as I said, ScintPi is a series of ionospheric scintillation monitors based on low-cost, off-the-shelf GPS GNSS receivers. The first version was developed by Professor Rodrigues and a collaborative from Brazil, Dr. Moraes, and they called the ScintPi one. This receiver was based on only GPS receiver, so it was only be able to receive GPS signals. Then when I joined the UARS lab, I started conceptualizing and also developing ScintPi 2, which now is a GNSS that is based on a GNSS receiver instead of a GPS receiver, and that allows the acquisition of more signals. And after the development of ScintPi 2, we started developing ScintPi 3, which is now also a GNSS, but instead of recording only one frequency, it records two frequencies. So it's a dual frequency GNSS receiver. The many features of this receiver can be seen in our website. If you are interested on them, you could go to scan that QR code, or go to the ScintPi website, and you will find many different characteristics of them. So I'm gonna go a little bit into how we manage to process the data that comes out from the ScintPi 3 receiver. As I said, this ScintPi 3 is based on a GNSS receiver, which is the ZF9P from ublots. The sampling rate that it provides is 20 samples per second, so it's good enough for the observations that we use. It has some drawbacks. For instance, the signal strength resolution is only up to 1 dB, but that doesn't limit us for calculations, as I will show in the future. The nice thing about this is that the cost of the parts for this little unit is around $560 per unit. And that includes an antenna, a GNSS antenna, and also a 50 feet of cable, RG50A, which is a good one. So what we do is we basically grab the raw data from the ScintPi, like coordinates, timestamps, position of the satellites, the carry to noise ratio of the signals, Then we also grab observables as a pseudo range or carrier phase, and we use them to compute ionospheric parameters like TC, S4, also timestamp this parameter in time. We do all this process in our servers, as I will explain later. Well, when we start, we send a unit of ScintPi 3 to Brazil, to a collaborator that has a commercial um, ionospheric monitor from the September. And in there, our collaborator was able to place in parallel or ScintPi 3 with a splitter, right? And make observations at the same time. Because at that time we were interested to compare how good are the observations. So we started doing some comparisons. For instance, this is a comparison of the S4, how good is the amplitude scintillation index. And here in the top figure, you will see two rows. One is the S4 in red for L1, or the first frequency of GPS. And in the second row, you will see a green curve, which represents the S4 for the L2, also for GPS. But behind those points, you will see a line, a black line, sorry, that basically is telling you the S4 provided by the September receiver. And as you might see, the S4 agrees very well for S4 values greater than 0.2, basically. So this is one example, but we also can do a correlation between different satellites, as you will see in the bottom figure, and you will see that the correlation actually is pretty good. The correlation coefficient is around 0.96 with a little bias, but it doesn't limit us to do, as I said in the beginning, observations of S4. We also compared the TEC. We were wondering how well the TEC provided by the ScintPi 3. And here I have different columns. The first column is showing data from the TEC coming from the phase and also coming from the code for ScintPi 3. The second column is showing data from the September receiver as the same way of the ScintPi 3. And the third column, we are comparing TEC coming from the phase difference. So since we are interested in relative variations in the ionospheric density, we basically are interested in how good is the TEC coming from the phase. So you may see that in the third column, the observations between the ScintPi 3 and the September are basically one-to-one. So this is very good for our kind of observations that we are interested in. If you want to know more about the comparisons and how good this receiver is doing, well, you could go to the paper that we have here in the bottom and see some more applications and also comparisons about them. So I want to start talking about the platform that we have for the distributed sensors. So at the beginning of this project, we envisioned that we will have several receivers, and these receivers will be deployed around different regions, right? So our idea is that this receiver will be able to send binary data or compressed data through internet to our server, and then we start applying this process. So the way that we did is we basically structure our server in different folders with different folders. And in these folders, the binary data starts to be uploaded. Then we have automate a process that basically grabs all the binary data, all the raw data to process the parameters, the ionospheric parameters that we're interested in, like the S4 and the TEC. Another good thing that we are doing with this server is that we allow all collaborators to download their own processed data. So once all collaborators install the ScintPi, they have some credentials that allows them to download these files, and they could start doing some analysis of the data. So with that platform that we developed, we start deploying ScintPis, ScintPi 2 and ScintPi 3. And the good thing about this ScintPi is that it's basically plug and play. When you receive it, if you have DHCP in your router, the ScintPi will grab an IP and will start collecting data and upload it to our server automatically. You don't need to configure anything. And we did like this because as a student, start with the Septentrion at one point, and I start facing some problems. But then I realized, oh no, this unit needs to be really friendly. So we started trying to do as friendly as possible. And with that characteristic, well, we were able to deploy many receivers around the globe. We have around 28 receivers. Some of them have some power and internet issues right now, but this is more or less the distribution that we have. So most of them are located in the northern United States, and their goal is to study mid-latitude scintillations, as I will show in further slides. Then we have some others in South America, low latitudes, and lower mid latitudes that are basically deployed there to study scintillations and all different type of ionospheric parameters, as I will show later. So I'm gonna do a brief summary of the things that I have been explaining up to now. First of all, this unit is a very low-cost solution, an alternative for ionospheric measurements. We have validated the TEC and S4 scintillation index against the Septentrion receivers, giving good correlation values. We have automated data processing and allowing our collaborators to download the processed data. We also have been able to do this unit plug and play, so we were able to deploy many of these receivers around the globe. And finally, as I said, our server is very secure. It uses a credential-based access to process to protect the data and encourage more collaborators to deploy ScintPis. So now that I have been talking about the description and development and the architecture of ScintPi, I want to start talking about the research studies that we have been doing with this unit. So I will start talking about the low to mid latitude scintillation. Why we are interested in low to mid latitude scintillation? Well, at mid latitude region, we have experienced scintillation. There are few examples of scintillation in this region. The one of them is from Levina in the early 2000s, and another one was published by Professor Rodrigues in 2021. The last reference that I mentioned suggests that this scintillation was generated by equatorial plasma bubbles or super equatorial plasma bubbles that are originated at the magnetic equator and then propagate and penetrate to mid latitudes. So historically, there are efforts to study the development of super plasma bubbles. However, to place ionospheric monitors in these regions, in the low to mid latitude regions, it's something very expensive because of the high cost of the typical ionospheric monitors. And part of our motivation is that we would like to also advance our understanding about when and how the irregularities of these large scale structures generate. And this is because we would like to perhaps mitigate the impact on our society. So that being said, we start collecting some scintillation observations in Puerto Rico. Puerto Rico is a nice, very nice area because it's basically in the middle of in the transition zone between low and mid latitudes. And we start doing climatological studies. we started doing collecting scintillation observations for different days, for quite geomagnetically quiet days. That is, the KP needs to be less than 3. And we do that for, in this case, 3 months, from December 21st to March 20, on the 22 from 22. Sorry, from 21st to 22. And what we found is something really interesting. In this area, we found a lot of scintillation activity. There are some days that we don't have scintillation at all, but most of the geomagnetically quiet days have scintillation. So this basically reflects this day-to-day variability of the equatorial plasma bubbles and scintillation. And this is a question that is still in our community. So we are basically trying to understand what are the mechanisms behind that occurrence rates. Well, we basically do some geolocation of these observations that we have in Puerto Rico. Here we have an example of the observations, and we basically study significant scintillation with the S4 index, which is greater, needs to be greater than 0.2. For instance, I have here an sample for observations that were done in December 26th of 2021. This is more or less at the time we deployed the ScintPi receivers in Puerto Rico. So we start doing some occurrence rate of these observations. We start doing what is the percentage or the occurrence of the likelihood to have scintillation at given time. And we divide the night time in different hours, right? And we start calculating or estimating what will be the likelihood to have. Basically, we count the number of S4 greater than 0.2 over the total number of S4, and this percentage we assign it to a beam, which is basically divided in 2.5 by 2.5 degrees latitude and longitude. So what we found is pretty interesting. The data, the occurrence rate of those observations starts early after sunset, early evening, and then start to progress in latitude as the night progresses. You will see, for instance, that between 2 and 3 universal time, the scintillation observations starts to appear around 22 magnetic latitude. And this is kind of a boundary for those type of observations on those conditions, on those solar conditions. So we basically was doing this study, and we would also want to corroborate that these scintillation were generated by equatorial plasma bubbles and not other type of irregularities. We use gold data to basically verify that, and we found that, well, all these observations are provided by equatorial plasma bubbles with the combination of the equatorial ionization anomaly that provides the background density conditions. So more information about this quiet time climatological study could be found in this paper that we have in the bottom. And then we not only study climatological quiet time observations, we also start studying some geomagnetically disturbed days. For instance, on March 14, on 2022, we have a disturbed day where the KP reached around 6. So in this day, we have observations of super-equatorial plasma bubbles. As you will see here, we have the gold data representing the background conditions for the ionosphere. And we will see here that the background conditions have enhanced background densities that allow the development of super-equatorial plasma bubbles. For instance, here we have a depletion, which is this black region above Puerto Rico. And if we plot the S4 observations, we will see that those S4 observations are basically on the gradients of these equatorial plasma bubbles. These observations were able or these scintillation observations were able to reach around 28 magnetic latitude, which is a really high altitude over the magnetic equator. And now we have a student that is basically studying or expanding that work, because as the time progressed, as we increase the solar flux conditions, we are starting seeing more activity. And now all the data is not bounded by 22 magnetic latitude, but now we start seeing scintillation that reach basically 28, 26, which is the same altitude that were reached by super equatorial plasma bubble under disturbed days, but this basically is under quiet times. So this is a current study that we are doing right now, and we are trying to identify what are the conditions for the development of these super equatorial plasma bubbles. So this is another summary that I did for this part. The plug and play capability of the ScintPi allow us to deploy monitors in Puerto Rico, in this Caribbean region, to start studying the scintillation occurrence rate in transition regions between low and mid latitudes. Initially, we found that all the activity was bounded by 22 magnetic latitude, but then we also found that we registered or recorded more activity above this or beyond this boundary. We also could complement observations like space-based observations like the used in the gold mission to see and characterize this area and to see how the scintillation is correlated with those observations. So now I'm going to talk about another type of study that we did with the ScintPis. This is called the sonar irregularity drifts, which basically retrieve information about the velocity of the irregularities in the ionosphere. So our motivation behind this is that measure the ionospheric drift is really hard. We basically at UT Dallas, for instance, there are a specific department that builds in situ sensors that develops sensors for in situ measurements. But these are very expensive. However, there is a tradition of measure the plasma background drifts using irregularities. This has been done with radars in the past, for instance. And also there is another technique that uses scintillation observations to do ionospheric drifts. But these require more than one ionospheric monitor. But now that we have this capability of low-cost receivers, we could use these low-cost receivers to try to derive this information. So to do that, we basically sent 2 units to Campina Grande in Brazil. And these units are basically placed in the magnetic direction, in the east-west magnetic direction. And since they have to be in the east-west magnetic direction, they are over buildings that have different height. For instance, this setup has a height difference of 15 meters. But that's all right because we could compensate that effect or that generates an effect on our observations, but we could compensate that as well. So how we study sonar irregularity drift? Well, there is a well-known technique that was introduced by Briggs et al. In 1950, and then it was improved by Levine et al. In the early 2000s. So this technique basically analyzes the apparent velocity of the irregularities with 2 receivers, and is called the space receiver technique. So this sketch looks very simple, but actually the scintillation space receiver technique has several considerations. For instance, one needs to consider the saddle velocity or the scan velocity to get the real velocity of the irregularities. We also need to correct to compensate for turbulence, or also compensate for the geometric corrections that due to the displacement of the receivers. For instance, the difference in height generates make us to do a geometric correction that we could find in one of the in the procedure of developed by Levine et al. In 2004. And also the turbulence correction could be corrected using the full correlation technique, which is also a well-known technique that Brits et al. Explained in around 1950. With that technique in mind, well, we could basically retrieve the ionospheric irregularity velocities, or in this case, the zonal velocities. This technique is kind of complex. However, we could simplify it using geostationary satellites. And as you may know, the geostationary satellite, for the geostationary satellites, the scan velocity is basically close to zero. So we could ignore some of the orbits that are used for to get the satellite velocity, which is kind of complex. So using geostationary satellites, we could do observations of ionospheric drift without all this, without messing with the complete technique. For instance, I have here an example. This is for October 4, 2022, in Campina Grande, of course. Looking at the satellite S-BAS 100 series seats. So this satellite provides, or little ScintPis are able to grab the information from the S-BAS satellites. And for instance, here I have 1 minute of data, this bottom figure. You will see 1 minute of data, and you will see that the black line is basically behind the red one. And this means the east receiver is detecting the scintillation pattern at a later time than the west receiver. So whatever is generating this fluctuation in the signal intensity is going from west to east. It has an eastward component. So we could analyze the signal and using cross-correlation techniques to estimate the time that is between these two curves. And with that time, we could get an apparent velocity because we know the distance between them, which is in this case 140 meters. We could do that for every single minute, but previous to that, we need to estimate the H4 index and also the cross-correlation coefficients between the signals. And the cross-correlation basically is giving us a parameter that tell us how good are these signals between between them, right? How close are in shape are them. And as you will see, the cross-correlation coefficients here are basically above 0.75, which is pretty good for given that we have 1 dB resolution in the signal strength. We also compute the S4, as you will see here in the panel B. You will see that the S4 basically represents the fluctuations of the signal intensity. And these fluctuations are similar between them. They have to be similar because they basically are within the same time window. So after doing these two, we could basically filter our data or raw observations based on S4 and also based on the cross-correlation coefficient. And if we filter then, we could then extract apparent velocities that we could correct for turbulence or geometric effects to give the zonal regularity drifts, which is the panel E in this case. So panel E is showing here how good the observations are and how well they correlate with the ionospheric background motion. You will see at the beginning of the night, we have velocities that reach 150 meters, and they start to decrease as the night progresses, right? Reaching around 50 meters per second. And also this is a positive velocity, which means an eastward component. So this reflects basically the background ionospheric motion of the ionosphere. And this is with one satellite and one single night. But we could also do this for several months of the scintillation season. For instance, here I have a plot where we show several months of S4, which is the top panel, between 6 and 2 a.m. local time. And you will see that these observations are basically from September to May. These are around 8 months of data. And in those 8 months of data, we only have like 7 days without data that are due to power outages. But for all that data we have collected, we have estimated the ionospheric regularity drift, as you will see in the panel B. So this ionospheric regularity drift have a nice way, a representation, and also higher values around December solstice, as you will see, and there are lower values around March equinox. So if we ask why we have this behavior, well, we could basically answer that question based on the neutral winds, because we know that the zonal ionospheric drifts are related to the neutral winds, or basically to the integrate weighted neutral winds by the Penderson conductivity. And this is an expression that we could find in a paper by Harendel now in 1992. So if we use a model like HWN14, horizontal wind model, we will around the same region at the same IPP, we will see that the horizontal wind model is basically has a similarity in shape and in distribution of these ionospheric vertical, zonal drift velocities. They are higher in December during December solstice, and they start to decrease around March equinox. However, they are not the same. One is the integrated version of the other, so we don't compare them. But if you would like to know more information about this technique and how we could use it for measure, I don't know, ionospheric drift over Africa, for instance, we could go, well, you can go to this paper and start looking how we implement this technique. That is only, that has been performed with only one satellite, which is the geostationary satellite, right? And this is, for instance, one night of this geostationary satellite. But we could also do this technique using different constellations, and also taking into consideration the satellite or scan velocity of many of these satellites, right? So if we take into consideration that, we will not be able to only measure S-bus, but we will also be able to measure different velocities. We could also be measured velocities using different constellations. For instance, here I have different panels where I show the drifts measured by the GPS, by the Galileo constellation, GLONASS, and the Beidou. And in the last plot here in the panel F, I see like, you could see like an average of these velocities. They also resemble the ionospheric background motion. I don't want to extend about this type of study because the time is short, but you could go to my poster of the last year and check more about this technique. Okay, so a quick summary of this research study. Beyond TC and S4, a local array of ScintPi monitors can provide ionospheric zonal irregularity velocities. The technique can be greatly reduced in complexity using geostationary satellites. But also we could get information using all the GNSS constellations. And another thing is that these drift observations could basically give us an idea or insights about zonal wind velocities. Okay, now I'm gonna go to our last uh, type of study we have been doing. This is about mid-latitude scintillation. And our motivation is, well, basically we have um, we have limit or activity of mean latitude scintillation up to of low latitude scintillation up to 28 magnetic latitude during quiet times. But right now I'm going to show you an example of mean latitude scintillation that basically occurs over Texas. So this example helps us to our understanding about what are the conditions for the generation of irregularity or scintillation over Texas. What is the mechanism behind it? So on March 24, 2023, we detect a case of intense mid-latitude scintillation. This is our receiver. This is the field view of our receiver in Texas. And in the bottom panel in red and black dots, you will see how was the S4, and you will see that the S4 almost reached 1, which is really intense for the scintillation conditions. The panels that you have in the top part, you will see, in these panels you will see that the scintillation comes basically from the south and then start propagating to the west. So at that day, we start looking at different receivers that we have in the American sector, especially the ones at lower latitudes, because the the scintillation activity detected by Texas was coming from this direction. So we start looking at our receiver in Costa Rica and also at Jicamarca. And we detect really strong scintillation over Costa Rica. We basically take more than 10 hours of strong scintillation that is greater than zero point 0.1. And this is over more than 10 hours. This is, we never saw something like this. It's very, very rare and very strange. We also detect some scintillation activity at the magnetic equator at the Jicamarca Radio Observatory. And all of these observations may have think that it was generated by equatorial plasma bubble or by a super equatorial plasma bubble reaching magnetic latitudes around 42. That is the location of Texas. So this is different snapshots of the scintillation activity showing the spatial temporal evolution of the super equatorial plasma bubble. We basically, at the beginning of this series of snapshots, we don't have scintillation at all. Everything is very blue. And then we start seeing some scintillation observations. So these observations start to populate Costa Rica between 1 and 3 universal time. And after that, they start to jump to mid latitudes. So we will see here in the second row some scintillation observations in, in the field of view of the receiver at Texas. And these are the ones that generate this scintillation activity in our monitor. So this scintillation activity reach Texas and they leave, but they persist over Costa Rica, as I said before, for more than 10 hours. So if we take a look at the DC data, we will see that the background conditions for the development of these superequatorial plasma bubbles were there at the beginning of the night. Here I have different rows. Each row represents one different day at the time of interest of the, or at the time where we found this scintillation activity. So basically on March 23, on March 25, the equatorial ionization anomaly was not spread as you could see on March 24. So this spread of the equatorial ionization anomaly helped the super equatorial, sorry, the plasma bubble to reach these magnetic latitudes. Okay, and this is because the plasma bubble will stop rising when the internal integrate density reach the internet background densities. So more information about this event you could find it in the paper that we have here in the bottom. Well, so I'm gonna do some a final summary. We basically have been using this low-cost receiver to do several type of observations and also studies. And it could give us information about S4, TC, and also the drifts. We could also study mid-latitude scintillation, deploying a bunch of them over these regions. And more importantly, give us education and opportunities to undergraduate students that are able to or interested in space weather and space science studies. With that, well, I finished this presentation and I will take any question that you have. Thank you.
Yeah, thank you very much, Dr. Gomez. This is really fantastic. Thank you so much. I enjoy all the sequence of results from low latitude equatorial region to mid latitude. I think the mid latitude one is more interesting to me. How you show the source of scintillation is actually coming from that low latitude region and reaching to the mid latitude in Texas. That is really, really cool stuff to see. I think we have some questions.
Mm-hmm.
Yeah, so yeah, Bruno has I think Bruno has a lot of questions for you. Do you want me to read it out, Bruno, or you will just take the floor?
Well, I can see the questions. Okay,
Okay.
here.
Can you see the questions?
Yes.
Okay.
So the first question is, how is the receiver binary data analyzed? Any future plans for the fair frequency in the receiver design? Okay. The binary data um, that we record is basically is a format that is created by our lab, and it helps us to the compression and also to send this data through internet. And we use Python libraries to read the binary data. There are some libraries that help us to do this. And if there are any future plans to include the fair frequency, yes, we have some future plans. We are currently studying different options to expand our observations. So on slide 15, I see the scintillation was detected on all constellations, and we talking GPS, Global Galileo. What's the scintillation balance on all the constellations? So let's see slide 15.
Mhm.
If the scintillation is balanced, well, I didn't take a look specifically at that. My understanding that balance in this case is if the occurrence rate is basically the same for all the constellation. That's a specific question that I don't know. I don't have in the top of my head, but I don't think so. Um, on slide 37, which particular SBAS can we think about in the African SBAS angle? Well, in the African sector, in the 37. Yes, in the African sector, I know that, for instance, this satellite SBAS 136 is around 20, if I don't remember correctly, it's around 20 east in the longitude sector of 20 east. So you could basically take those observations that will have high elevation angle to retrieve ionospheric drift information. We think about the African. Yes, and I also know that there are also several other satellites, geostationary satellites in that region, but we don't have an observation, and we didn't take the time actually to take a look at that region with one of our receivers. But I believe there will be some satellites providing this fit set reduced scan velocity. I believe that's are all the questions that we have in the chat. I don't know if somebody else have other type of question.
Yeah, do we have other question in the house? Just do you try to?
Yes. Hello.
Okay, go ahead, Dr. Emmanuel.
Yes, I have a question.
Mhm.
Thank you for the presentation, Dr. Gomez. I'm just interested in how the use of this particular monitor, how effective it will be within the African sector in monitoring, especially the equatorial sector of the ionosphere, in monitoring the scintillation in this sector. Because despite it being very affordable and easy to deploy, we still have some challenge in using it, such as the single frequency limitation and its level of sensitivity to several other scintillation and the quality of the data it can produce. So I want you to speak to this question.
Okay. So as I show in the beginning of the presentation, the resolution for S4 and for TC is pretty good. 20 samples per second, I believe, is also a good sampling rate. And in Africa, for instance, we had one receiver in Zambia. Yes, in Zambia, but it faced power issues because I believe the electricity is not as stable as in other countries. However, Jonah already have the idea that these receivers needs to be solar powered. Here we have a group of students that developed a solar powered ScintPi in the past. And if you dimension it correctly, I believe the ScintPi could run like for more than 4 years, which is the time that the receiver is running in the field. So it's very feasible to have continuous observations of the ionosphere, but we just need to take into consideration the power issue that we might be facing and also the internet issues. Another nice thing, I'm really glad that you asked this, is that the transmission of data. Usually, the current version of the ScintPi is transmitting binary files. However, there are efforts, right now we have efforts to reduce these binary files to different formats to allow real-time observations with a minimal using a minimal bandwidth over the internet. So this is basically right now doing by a group of undergraduate students that we are helping with this. And I believe in the future we'll have a new real-time capability. That answer your question?
Yes, thank you very much.
Mm-hmm.
Then we would need, in order for it.
Sorry?
Dr. Emmanuel, we lost you. Maybe you want to chop in later, back on. But I think we also have questions in the chat now. I want to tell us that we are a little bit above the hour, but we usually take more than 10 to 15 minutes to discuss and ask questions. So no problem. All right. So if you have questions, be brief, and then we can all reach everybody with their questions. So Jose, I think you have some questions in the chat again.
I'm trying to look the chat. I can't find it now.
Okay.
Could you read it out, please?
Yeah, it said besides the scintillation, can one use it for positioning purposes? that is your ScintPi? Can it be used for positioning purposes?
Well, my understanding is that for positioning, we use different techniques, right? And since the observables are pretty coherent with observations provided by other type of receivers, I believe it could be used for positioning. There are some papers out there in over the internet that you could find that talks about the limitations about the receiver for positioning, but I saw some results and I believe they are pretty convincing. You could rely on these receivers for that.
Excellent. Okay. I think more discussion is on that, maybe in some other meetings. Okay, so but I think Dr. Bruno also have one more question here. What is the signal strength power range for these receivers?
So
Okay, go ahead.
yeah, this receiver is able to acquire up to 56 dBs, um, dB per hertz, right? So if we use, for instance, an antenna that has a lot of gain, like some folks have been doing, the signal will be saturated. Okay, but if you use a low cost antenna that doesn't have a lot of gain, the receiver will be able to handle the signal and to acquire it to without saturation. So this is it's not a limitation, but it's something that someone needs to consider in the design of the whole system.
Okay, so I have another question from Yenka. Yenka is from ICTP.
Mhm.
She's interested in, said, thank you, Josemaria, for the interesting presentation. Can you share the approach to developing the receivers?
Yes, all the instructions are in the website. So I share in the you could scan this QR code and go to the ScintPi website, and in there are guides on how to do ScintPi one, for instance, step by step. And we have the firmware, we have the parts that you need to buy, everything there. So you could basically start building this version and then expand to the other ones you want.
Excellent. I think there's a subsequent question. Okay, follow-up question from Yenka. I mean, this distribution. How do you decide where to install them?
How we decide? We don't decide. We basically rely on collaborators. Every time the collaborator shows up, they ask if we could give us a ScintPi unit, and depend on if we already have one there or not, or if we have ScintPis available, we could send one to that region. That's how we start populating um, this with this map. We don't decide. We basically have some collaborators that show up, and that's how we did it.
Oh, okay. So that depends on funding availability. That's what you mean, right? Okay.
Yeah.
So, and Dr. Bruno is also asking if this can go real time. I think there's a question about real time.
Can you read the question, please? I
Okay, he
don't.
said, can one monitor it in real time?
Yes. Right now, we have students that are working this real-time capability, and we are developing that feature. So I believe in the near future we will have real-time capabilities for monitoring S4, RTI, and maybe the drips as well. Mhm.
Excellent. I think, let me see. Some correlations. Oh, okay. Okay, no problem. Thank you for that notification.
I'm
Uh,
having.
I don't know who is this. Dr. Emmanuel is also asking a question. Do you have the chat with you? You said?
Yes.
Okay. Do you see the question from? Dr. Emmanuel?
Mm. I can see the questions
Okay,
here.
so I can read it. Is it a question or a statement?
I believe it's just a comment.
Comment, okay.
Yes. African region has varying for monitoring to compare to region. So high concentration to receiver to high data quality. Yeah, I believe it's more like a comment than.
Okay. So this map you are showing currently, it shows your distribution that Madam Yenka was talking about. And this is a nice distribution over Africa, South and North America.
Mhm.
And I see in your study you try to show the effect of this distribution of scintillation in a particular event.
Mm.
And that is one from the mid latitude. And then you show the one in the low latitude and equatorial region. That is
Mhm.
really cool. Do you seem to have a receiver at mid latitude over Africa? Do you do the same kind of study for that you did for Texas? I think they're around the same latitude region, latitudinal region.
Oh,
Is it?
well, I believe it's around 45 magnetic latitude, a little bit higher, but we didn't pay
Yeah.
attention to the data. Yes.
It will be
We
interesting to see if you see the same kind of transition from that region. Those intelligence
well,
actually coming from the equatorial region rather than how
mm,
people think they are coming from the polar region or
the
so.
northern,
Yeah.
yes.
So that's
We
really something to check, all right?
we didn't were able to analyze all the data. That's data that needs to be very carefully analyzed, right?
Yeah.
Because to look at that portion, we need to discriminate if it's multipath or not, if we have multipath, and also during geomagnetic disturb days. But superquaternion plasma bubbles, they don't always occur during geomagnetic disturb days. They depend on many factors. So it's a study that it really needs someone to sit down and take a look.
Excellent. Thank you so much. Is there any other question in the house? Anybody with questions that wants to take the floor? I think I like this discussion a lot. In this meeting, we don't usually finish with discussions. There is always something interesting to come back to. And this one is definitely I have multiple things here to come back to, like the positioning. Can the receiver be used for positioning? And, the scintillations in different places, how do they compare? Where are they coming from? We see one from over North and South America, but this could be done in several other places, right?
Yes.
So, very interesting results, you say. I really appreciate your talk today. It's been wonderful. And we thank you for coming to join us today at CONGA. And anyone in the house want have the final comments? Can you stop sharing your screen?
Yeah.
Nico?
Thank you, Jana, for inviting me. I am
Uh,
glad to share my results with you guys.
yeah, sure. Yeah, it's what we do here. We want to educate people on some of these things, and uh,
Mhm.
you have done that very perfectly today. And,
Thank you. Thank you.
so, lastly, I just want to show us that we have Dr. Andrew. Dr. Andrew, you are in the house, right? This is our very um, consistent person here. It usually inspire me to continue with the CONGA meeting in the early stage. Before we open the floor, he's already on the floor. He's always the first person to attend this meeting, and I appreciate him a lot for this. So last month, he contacted me that he has some results to show on TEC and what he has been doing on some instrumentation. So we'll be having Dr. Andrew for our September 24th meeting. So Dr. Andrew, if you could send me the title of your talk, and we will communicate as well on maybe you want to send me some abstracts and your biography and things like that for the talk. And on next month, which is our next meeting, we're going to have my very good friend, Dr. Dima Mondor. We actually had a postdoc together at MIT A-Stack Observatory, and he has been working on instrumentation across the Arctic region. He has been doing a lot of interesting studies and handling and installing instrument sensors across the Arctic where there is snow, and they have a lot of interesting things to talk about. So I've invited him to join us to be our guest speaker for next month, which is on the 27th of August. So I don't think you want to miss that. You can please invite your students and other people that you may feel they should listen to these educational talks. With that, if there is no other question, we draw the curtain here, and I want to thank everybody. I see a lot of people that I know here. I'm very, very grateful for everybody that comes to join us for the meeting. I see Lindsay, I see Yenka, I see Manuel, Dr. Bruno is there, Bruno Navas, and yeah, a lot of people that I've met in person that are here, and a lot of people that I've not even met in person. I wish to meet everybody. I think Aston here, Aston is also working on receivers, small scale receiver in Canada, and we have had him before. He has presented some of the things he is doing. Very soon we'll be inviting him again to give us some updates. And with that, I think a lot of Africans, universities, professors are also here. And very soon, we will also invite them to talk about some of the things they are doing so that everybody can be on the same page and we can all collaborate together. So with that, I want to thank you all, and we will see you again next meeting. And thank you, Sheon Adeniro, for helping me today to be the host. And thank you for your consistency in admitting those people, or all the people that are here today. Yeah. So
You are welcome, sir.
you're welcome. No, thank you. So with that, I will close the meeting. Thank you. I will see you August 27th when we will bring another edition of CONGA meeting or series.
Thank you.
Thank you. See you then.
Yeah, thank you. Bye.
Hey.
Thank you all.
Yeah, good to see you. How are you?
Good. Doing
Yeah.
well. Thanks. See you next time.
See you. Yeah.
Bye-bye.
Thank you. Thank you. Yeah. Bye. And I think it should record on my system. I'm going to close the meeting. Thank you all.